Okay, looks like we're back. Maybe it's a different site. Whoa. And we're down again, are we? Okay, looks like it's hanging on here, so we'll just keep going. Looks good over here. Thanks, Sam. All right, let's try again. We've gone through this. Oh, no, this is a new one. Yeah, we just did that. Let's see what long question we have here. That's an easy one, so we'll skip that one. We've done that one already. So let's close that down. Let's go for January 19th. I'll start recording over here as well. Okay, so moving on to January 19. Let's see what we've got here. Ah, perfect. Okay, we've got a nice question here. Check the short questions. What are the 5 layers? We know that one. What's the difference between a recursive query and an iterated query in DNS? You don't need me to do that one. You can just check the notes for that one. That's an easy one. What type of DNS servers exist? Well, you know that by now. You got your root, you got your TLD, you've got your authoritative servers, and sometimes you got your local DNS cache as well. Why does DNS caching speed up internet access? Because it means we don't have to go to the trouble of contacting all those other servers to resolve a name in many cases. In message coming in on Teams. Okay, all good. Let's see, live streaming. Still okay over there, guys. I still have a decent output here, so I'm going to keep going. Bit turned. Suppose Alice provides chunks to Bob. Will Bob necessarily return the favor and provide chunks to Alice in this same interval? Why or why not? Well, we know from the peer-to-peer protocol that when someone comes along for the very first time, let's say Alice, she's going to have to try and connect to some people. They might not reciprocate necessarily. So it's possible that Bob has just, or Alice has just unchoked Bob for a period of 30 seconds. Will Bob return the favor? Well, if he's not impressed with the bandwidth that she's providing him, he's not going to add her to her top 4, and so he may not necessarily return the favor to her. Okay, let's go on to the long question. This is the kind of fun one. Okay, so so consider this network. So this is a long question. I'm assuming everything's okay on YouTube. So consider the networks shown in the figure. There are two user machines down here, M1 and M2, and they're both on this network down here. Suppose the user at M1 types in this URL here. They want to get a big file, say, from this server up here, B. So b.com, and this is the name of the path, bigfile.htm. I must have left out an L there. It doesn't matter. Into a browser to retrieve a 1 gigabit file. So there's a file up here. One of these guys is going to try and get it in a second. Let's see what the questions are. So A, list the sequence of DNS and HTTP messages sent and received from by M1, as well as any other messages that leave or enter the A.com network that are not directly sent or received by M1. Okay. Indicate the source and destination of each message. You can assume that every HTTP request is first directed to a cache in the A network, and that the cache is initially empty, and that all DNS requests are iterated queries. We'll assume the cache is empty. Okay, so you've been asked to list everything that's going to happen here once M1 makes that GET request to get the file here from B. Okay, so have a think about that for 1 second. I'll just get the board clear. So this is one of my favorite questions of the question ones that I've done so far, because it means that everybody, or if you can answer this, it means that you completely understand all the really important stuff about HTTP caching, as well as all the important stuff about DNS and DNS caching. So it's a real tester of a question. All right. Okay, I need to somehow get your messages here on the screen, so bear with me. Okay. So let's draw the network here. We've got our M1 down here, so on the A network down here. So just here we've got two nodes, M1 and M2. And we've also got our DNS cache and our HTTP cache. So I'll just use a different color there. So our DNS cache was over here. That's our DNS cache, and we've got our web server over here as well. So a web cache. Okay, so they are all linked together onto some high-speed local network, like your Ethernet, for example, on your campus or wherever. And then we get to our gateway router here. Then we've got another router over here, which links to the B network up here. So I've got two more servers up here. I've got the actual server we want to contact, so that's b.com, and over here we've got the DNS server for B, the authoritative DNS server for B, and that's on a separate network over here. So remember, as we discussed in DNS, once you set whatever, let's say you set up a university or whatever, you're going to have a web server on site, presumably, unless you're paying a third party to host it for you. You have your web server here with all your URLs stored here and all the files, and on your network will be a mail server, and also on your network will be a DNS server, which will manage, it'll keep track of all the IP addresses for all the different hosts on your network. In this case, it's pretty easy, right? There's only one host, but there could be thousands of hosts here on your network. Okay, so you've been asked to list the series of actions. So I'm going to list them over here. So M1 is going to make a request for M1 is going to make a request over here to get this web page up here, web page from B, and you've been asked to list all of the sequence of actions that take place in order for that to happen. And this is, like I said, this is a real tester to see if you understand what's happening at the application layer level. So the first action, so let's just put down here a long list here. So we're going to have lots of items on this list. And so what's number one? Number one is going to be so the first thing that's going to happen is you're going to set, so the user is going to type in the name of the URL. It's going to type in the URL into their browser, their Chrome browser or whatever, and then hit enter. But so a GET request is not the first thing that will happen here. A HTTP GET request. The very first thing that will happen is M1 will realize it doesn't know the IP address for the URL that's just been typed in. So it needs to use DNS to find out what that mapping is. So we're going to send a DNS query. So DNS query. So M1 sends DNS query to this local DNS server down here, okay? To local DNS server. Can you guys read that? Is that too small? Do I need to make it bigger? Let me know. Can you just let me know there, and I can check the messages? So if anyone could just let me know that this is legible, that'd be great. Or that there's anybody there at all. That you're still here. I've only got 17 viewers. That is disappointing. Anyway, can one of you 17 just send a message to say that it looks okay? Of course, there's a lag here, so you're probably only hearing this in the future. I'll keep going, but I'd really appreciate a message. Right, so that's the very first thing. M1 is going to send a DNS query to the local DNS cache here. So the DNS query will end up here. Then this cache will take on the responsibility of finding out what that mapping is. So the DNS server will send, so number 2 here, local DNS on this network here, will send the query, will send query to root DNS, So I'm getting some. Looks good. Great stuff. Okay. Number 3. Your root DNS sends DNS type equal to name server to the cache, to this cache down here, to cache. 4, you're going to get this will then send the query to the TLD DNS server. To TLD. We've got the TLD sending back to the local DNS. Finally, we'll say the local DNS can now send a type A. Type A, so I just put an A here, to DNSB up here. Then 7, DNSB sends back type A answer to local DNS. Okay, finally now, after 8 steps, the local DNS can send the authoritative answer back to M1. What else have we got? So only now does M1 actually know the IP address for the URL that it wants to send a GET request for. So now M1 creates the GET request. So number 9, M1 sends GET request, HTTP GET request to its local web cache. And we'll assume that the web cache does not have the file stored. So then the cache sends the GET request up to B. Then B returns with the file. So you can see there's a lot of actions that actually take place here. B sends the file, so HTTP response, HTTP reply message. To the cache. Finally, number 12, the cache sends the file HTTP reply to B, or to M1. Okay, so you can see the list of things there is quite long. The list is pretty long. Let's just check which ones were DNS. So this was, let's put in the type of message here actually, why not? Message type. This is all application layer message type. So this was a DNS query. DNS type, DNS query. Type A, we're looking for an authoritative answer. Local DNS sends DNS query type NS to the root, get back a reply. DNS reply, a response message, type NS. Then we send another one of these, DNS query which is also type NS. Comes back from the TLD, DNS response, type NS. Then we finally said a type A. So DNS request, or DNS query rather, type A. We get a reply, DNS reply, a response, type A. Then that gets sent back, so it's just that's just a repeat of the above one. And then we can send our HTTP get request. Then we've got another HTTP get request. And then we've got HTTP file response. It's type 200. What's the good one again? Type 200 OK. HTTP 200 OK. And HTTP type 200 OK. So that's all of the possible messages that are gonna happen here. The reason I've done it like this, so the reason I've shown it like this, because we're going to show the times for each one of these in a second. And like I said, this is a great question. It really tests out your understanding of all of this. And I suppose I can just show here for these, if anyone can remember what's actually happening here for these first 8 steps. What's actually happening here is we've got our DNS server, we've got a M1 here. M1, it sends a message to the local DNS. And then he sends the message to the root. He sends the reply back. So this is, and then this goes over here to the TLD. That comes back. Then this goes over here to the type A. And we get the response back. And then finally we go here. So 1, 2, 3, 4, 5, 6, 7, and 8. So that's the first 8 steps that are actually happening here. And if you can't remember this, you can just go back to the lectures. I did this in a really nice graphic in the lectures to show you what was happening. Where are we? Oh, great. Thanks. What's next? Yeah. Okay, so what was the next part of the question? So list everything that happens. We've just done that. How much time does it take to accomplish the steps you outlined in this question? Explain how you arrived at the answer. In answering the question, you can make sure the following subjects: the packets containing DNS commands and HTTP commands are very small compared to the size of the file, and thus their transmission times is just could be neglected, but not their propagation times. That's important. And what else can we say here? Propagation delays in the LAN are small enough to be ignored. So we've said the propagation delay down here is 0. I better write these in here in a second. So propagation delays within the LAN are small enough to be 0. Propagation from router R1 to R2 is 100 milliseconds. Propagation delay to and from anywhere in A.com to anywhere else in the internet is half a second. And you can neglect TCP handshaking. Okay, well that's handy, because if we had to put in all the TCP messages for a connection setup, that would be a pain. So let's go through it. Let's go through that on the board. All right, let's just put in all the times we can, all the information we can into the figure. I hadn't done that yet, so now's the time to do it. So you're told down here, so this this link here is 1 megabit per second in both directions. So 1 megabit per second, and that's your, we'll call that OR2. We'll call this OR1 down here on this link here. So you're told OR1 is 1 gigabit per second LAN, so that's probably your Ethernet, 1 gigabit per second. What do we say in the top? 1 gigabit per second up here too. So this is 1 gigabit per second too. So that's OR3, we'll say. What about your propagation delays? You're told that you're told your file is 1000 megabits, so 1 gigabit file. So the file that you're requesting up here, file inside here, file L is equal to 1 gigabits. And what other information do we have? We have propagation delays. You were just told in the question. So the DNS commands, HTTP commands are small size, so we don't need to think about the propagation delays. You also told the propagation delay between OR1 and OR2 is 100 milliseconds. So we'll just call that P2 here is, when I say 100 milliseconds, 100 milliseconds. And you're told that the propagation delay to anywhere else is half a second. Okay, so in other words, why is that important? Well, all these guys here are anywhere else, right? So all these guys are going to have propagation delays. I'm going to call it P3 here. P3 is equal to 0.5 seconds or 500 milliseconds. So that's important. So we've got this propagation delay here, and we've got 0 propagation delay. So all these links are going to be half a second propagation delay. Other than b.com, and that is the propagation delay down here is 0. So P1 equals 0, and P3 here is equal to 0. I'm going to have to change my name here, so I'll call this P4. Okay, so what's the total time to get the file? Let's just check you guys are still there. It looks like everything's running okay. Super. All right, let's go through the times to get the file over here. So delay. Here. So M1 sends DNS query to local. Remember, it's always transmission delay. It's always trans delay plus propagation delay. That is always the way it works. So it's always L over R plus whatever the delay is, the propagation delay. So what have we got? This first one is just a DNS small message that goes straight to the DNS. So we're told that the message size is 0. So this is going to be 0. 0 over R is 0. And we're told the propagation delay is 0. So super. So this is immediate, approximately instantaneous. Number 2, local DNS sends query to root DNS. So this is this step here. Bang, that's a 0. Again, our transmission delay is 0. But our propagation delay is 0.5 seconds. Same story coming back. 0 plus 0.5 seconds. So then the local to the T. It's the same story for the next one. 0 plus 0.5 seconds. 0 plus 0.5 seconds. What's next? 6, local DNS authoritative. So again, okay. So this is to the authoritative server up here, but you're told the propagation delay is 100 milliseconds here. So so this one this propagation for 0.5 seconds only applies to these 4 messages here that are outside of the network, other than A to B. So this one, this one, this one, this one are all 0.5 second delay. This one is 0.1 second delay, or 100 milliseconds. You're told that it's 100 milliseconds here. So this is going to be 100 milliseconds. It's going to be 100 milliseconds. So what have we got? We've got the transmission delay is still 0 because the message is so small, plus 0.1 seconds. That's 100 milliseconds. Same coming back, 0 plus 0.1 seconds. And then of course the message is coming back from our local DNS server back to M1, but we already know, same as this one up here, it's going to be 0 because the file is so small, and your total propagation delay is 0 as well. So if you add up all of those, that gives you the time it takes to resolve your DNS query. It's quite interesting actually. I don't know if I'll be able to do it here. Have I enough room on the board? I'll just do it here. So the DNS query, just DNS alone, takes half a second, half a second, half a second, half a second. That's 2 seconds, 2.2 seconds. Interestingly. Okay, the next steps will be a bit different. So we've got our GET request coming out. You're told that it's really small, just like your DNS. So you can put down transmission delay of 0 here because it's so small. L is approximately 0. The propagation delay will be the propagation delay will be 0 for this part of the network. So 0 is the propagation delay 0 plus this part 0.1 plus 0 here. So it's just 0.1. So it's just 0.1. The web request coming back here with the file, the 200 OK message coming back with the file, this is a different story altogether. Okay, so we're going to have to calculate that one a little bit differently. So the file size is pretty big, right? It's L, but it has to travel over this link, or 3, has to travel over this link, or 2, has to travel over this link, or 1. So there's going to be 3 different transmission delays there we're going to have to add together to get the answer for this transmission delay part here. I'm running out of space, but I can do it. So it'll be L over or 3 plus L over or 2 plus L over or 1. So that's your transmission delay over here. And your propagation delay will be 0 plus, so same as the last case, plus 0 plus 0.1 plus 0. Okay, so our propagation delay here, if anyone wants to work it out, that's 1 gigabit per second into 1 over R3, which is 1 gigabit per second. So that's going to take 1 second, right? We're dividing 1 gigabit per second by 1 gigabit per second, or 1 gigabit by 1 gigabit, so that's going to be 1 second. So that's 1. What about here? It's 1 megabit per second. So it's going to take 10 seconds, right? So if I divide this by this number, I get 10 plus 10. And then finally, it's the same as for the first link. It's just 1 second. So that's 12 seconds, and this is 0.1. And then finally, to get from the cache over to here is just 1. We know the propagation delay is 0 plus what's this one? This is a gigabit per second link, so 1 second. So L, so it's just L over or 1 equals 1 second. So it's 1 second down here. So let's just circle all of those, the important bits. So our DNS was 2.2 seconds to get down to here. So it's 2.2 seconds to get to here. And then we have 0.1 here, 12 here, 0.1 here, and 1 here. So in total we have 0.1, 0.1 is 0.2, 12, 13.2. So the file is 13.2 seconds. So the total time then is this plus this gives me 15.4. Oh, you can't see it down there. 13.2. I'll write it over here. So 13.2. DNS was 2.2 seconds in total, and your HTTP part was 13.4 seconds. So you should be getting those answers if you've done it the same as me. I hope. Any questions coming in here? No? Okay. Any questions there on that? Now you might be thinking it's a really long question at this point, but if you've done it the way I've done it, the next parts are really easy. That you just get the answer straight out. So let's test out the next part of the question. maybe it's a bit of a long one, to be fair. To be fair. Now assume that machine 2 makes a request to exactly the same URL. List the sequence of DNS and HTTP messages sent and received by M2. Okay, so the question is, what happens now so if M2 comes along and makes a request for the exact same file from the same with the same URL at the same IP address, what's going to happen? What's the sequence of steps? So it's actually quite straightforward. I can rub out a bunch of these steps here, and D is just test how long it is. So let's do both. Okay, so the question is, look, B is going to come along now, or M2 is going to come along and request the same file. So let's go through it. So this is part C and D. Okay, so I'm going to rub out bits here. This is part C and D here I'm about to do. Alright, so what are the actions? Very first thing is M2. We're dealing with M2 now. M2 is going to send a DNS query to the local cache, type A. Takes 0 seconds. Super. Then the local DNS is just, it has it. It's going to realize it has it already. The TTL has not expired. So it doesn't have to do any of this stuff. We can just skip down to step 8 here. The local DNS replies with the authoritative response to M1. It's a type A DNS request. And that's going to take 0. 0. Did I not write that down? 0 seconds anyway. I must have left that one out. It doesn't make a difference. 0 plus 0. So let's just do that. So I'm going to rub out all of these guys. I don't need any of these. So steps 2, 3, 4, 5, 6, 7, all gone. Straight down to skip to step 8 because the cache has it already. Doesn't need it. Doesn't need to send it again or to look for it again from the TLDs and so on, from the root and so on. So skip straight to the end. Alright, so our 8th step is actually now our next step. It's step 2, but I'll just leave it as 8 here. And we don't need any of this either, so we can just I'll just cross it out to save time here. Gone, 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 gone. So what's our total DNS time now? It's not 2.2 anymore. It's dropped to a whopping big 0 seconds. So we've saved 2.2 seconds right there just by using the cache, by having that, and that's actually a fairly accurate representation of what happens when you use your browser. If the IP address is already stored in the cache, it's about 2 seconds faster, or can be, depending on where the authoritative and where the root servers are that you're contacting. So anyway, so we've skipped down here. Great. Next step, M2 is going to contact the web cache with the GET request. HTTP GET request, and that's still going to take 0.0. This time the web cache is going to realize that it has a copy of the file stored, but it doesn't know if it's an up-to-date one. It doesn't use a time to live like DNS. So instead of sending a normal GET request on behalf of B on request of M2 up to B, it'll send an if modified send. So it'll send a HTTP GET. This will be a GET. This will be an if modified, or a conditional GET. This becomes a conditional GET request here with an if modified. with an if modified. So that's a conditional get. So I'll write down C get here as well. Okay. Then the B it'll just reply with HTTP reply. What is it? 30. What is it? 403? Is it 403? I can't remember. I think it's 403. Whatever the one is for, you've already got that one. I can't remember. No, it's 200 OK, but it has. It's 200 OK, but it has a. It's still 200 OK, yeah. Or is it a different number for a not modified since? I can't remember. Anyway, it's a small detail. So that comes back, but this time there's no file. This time it doesn't contain the file. It's just a simple response saying not modified. So we just get rid of this entire download over here, this download time. So that becomes 0 because we're told that small messages can be ignored in terms of transmission delay. So that becomes 0, and we still have our 0.1 over here. So now we have a 0 here plus 0.1 propagation delay, and then finally we get we actually get the file back. So sorry, we don't need that 12 seconds there anymore. Any of that, it's all calculated. It's all 0 now. So the file coming back still takes us a full second to get from the cache over to M2, because that's 1 gigabit per second divided by 1 gigabit per second bit rate. So we still get L over R1 equal to 1 second and a propagation delay of 0. So the overall time now for the file, so this is 0 by the way for DNS, so we can rub that out. We calculated that up here to be 0. And now we've got a total time to get the file down here of 0.1 plus 0.1 plus 1, so 1.2 seconds. So our time has changed now to be 1.2 seconds to get the file using HTTP, and 0 seconds here. Total time to get, thanks to our 2 caches. Our DNS cache saved us 2.2 seconds, and our web cache saved us 12 seconds. So overall, we've got a reduced down to 1.2 seconds in total, and that's the saving you get from having these 2 caches working for you. And that's the end of that question. So I think that's a great question, because it really shows, you know, so much stuff about the application there, how everything is working from when you hit that browser, from when you hit enter on the browser and put in a URL. Okay, where are we at? We've got 10 minutes left. Maybe we can pick a few short questions.